Hello everybody, it's Tarun. Welcome to your 14th tutorial in the Signal System and Control course. In this tutorial, I'll start with Unit 4, in which I'll teach you about the discrete time Fourier transform. Okay, and in this unit, we'll learn the frequency domain methods for discrete time signals and systems. Okay, and what is the outline or what I'll cover in this unit is that firstly, I'll teach you a discrete time Fourier transform, okay, general, and then the discrete time Fourier transform for periodic signals, okay, which will include two categories. The discrete time, the Fourier transform for sinusoid signals is just a bit different than other periodic signals, and then the properties of the discrete time Fourier transform. Okay, this is the most important thing in this unit, okay, other than the duality. Okay, and the properties which I will be teaching you are somewhat similar to continuous time properties, continuous time Fourier transform properties, but there are some more properties in discrete time domain, okay, where we'll get to know them when I'll teach you to them. Okay, and there is convolution property and multiplication property similar to the last unit. Okay, and then the last part of this unit will be frequency response and linear constant coefficient difference equations. Okay, as I have told you earlier that in case of continuous time we consider the differential equation, and in the discrete time we take the difference equation. Okay, so now let's get started with the discrete time Fourier transform. Okay, so we are taking a periodic signal, say x of n, okay, and we are constructing a periodic signal x cap n or x bar n with x bar n equals to xn over one period. Okay, these are things which we are trying to do to connect the discrete time Fourier transform with the continuous time case. Okay, if period tends to infinity, then x bar n will be equals to x of n over any finite time interval. Okay, and then the Fourier series representation of x bar n converges to the Fourier transform of xn. Okay, we are considering a signal xn where xn equals to 0 when outside minus n1 and n2. Okay, as you can see here, and its corresponding periodic signal x bar n will be this signal taken as periodic. Okay, where it is repeatedly being grown in the spectrum. Okay, so obviously you can see that when x bar n will be equals to x of n when capital N tends to infinity. Okay, so now let's see it in the frequency domain, how we will derive the discrete time Fourier transform formula. Okay, let's consider x bar n is having the Fourier series representation in this manner. Okay, and its Fourier series coefficients a, k are these. You can find out these with the formula which I have told you in the discrete time Fourier series representation. So here if I take n here, then it will be n a k equals to minus n1 to n2, which is its time period, xn e to the power minus jk 2 pi by n small n. So and I can take it also to minus infinity to infinity to make it comparable to x of n. Okay, because we are here taking x bar n and we want to compare it with x of n to get a desired result. So I have replaced the value of n1 and n2 with infinite. Okay, and I have replaced k 2 pi by n with omega or k omega naught with omega. So here you can see that x it will be x of e to the power j omega for omega equals to k omega naught, which is the Fourier transform representation of discrete time case. Okay, so here you can see that x bar n is summation k equals to one time period of n 1 upon n x of e to the power j k omega naught e to the power j k 2 pi by n into small n. How did I do that? Because I have already found the value of ak, which is 1 upon n x of e to the power j omega. So here I have replaced just ak with that value only. Okay, so here you can see that this is the similar equation which we saw in the eigen value or eigen function, which I told you in the Fourier series representation. Okay, now when n tends to infinity, okay, this n tends to infinity, then omega naught tends to 0 because omega naught is 2 pi by n. Then summation becomes integration, k omega naughts become omega and omega naughts become d omega. Okay, and the summation over n intervals of width omega naught is equal to 2 pi by n will become integration over interval 2 pi by 2 pi, and x of e to the power j omega into e to the power j omega n is periodic with period 2 pi. Okay, for any interval of length 2 pi. Okay, so this was just a derivation for the discrete time Fourier transform formula. So here we can see the formula. Okay, x of e to the power j omega is the representation for discrete time Fourier transform of any signal, which is equals to summation n equals to minus infinite to infinite x of n e to the power j omega n, where x of n being the discrete time signal, and its inverse discrete time Fourier transform is 1 upon 2 pi integration over interval 2 pi x of e to the power j omega e to the power j omega n d omega. Okay, as I already told you, x of e to the power j omega is referred to as the Fourier transform of spectrum x of n. Okay, the shorthand notation is similar as it was in the case of continuous time case. Okay, here you can see that all the three shorthand notations are same. Okay, and there are some differences between continuous time and discrete time Fourier transform. Okay, which is in the periodicity of discrete time Fourier transform, x of e to the power j omega, which is there, and finite interval of integration in inverse Fourier transform. Okay, earlier in continuous time case it was from minus infinite to infinite, but here it is over an interval of 2 pi. Okay, and one more thing to note, that the Fourier series coefficient of ak of the periodic signal x bar n, they are equally spaced sample of Fourier transform x of e to the power j omega. Okay, as you can see here, ak is the equally spaced samples of the x of e to the power j omega. Okay, and x of e to the power j omega is the Fourier transform of the aperiodic signal x of n. Okay, now let's see some examples. Okay, first we are taking a signal where x of n is a to the power n u of n. Okay, u of n, as you all remember, it is the unit step function for discrete time case, and we are here given a constraint that mod a is less than 1. For the Fourier transform x of e to the power j omega, it will be summation n equals to minus infinity to infinity x of n e to the power minus j omega n. Okay, since the function u of n is valid only from 0 to infinite, okay, then the summation limit will change from 0 minus infinite to infinite to 0 to infinite, as you can see here. Okay, and the u of n will no longer be required. So here it will be a e to the power minus j omega to the whole power n. Okay, which I can reduce to this expression with the help of infinite summation of gp, which is a geometric progression, which is 1 upon 1 minus a. Okay, so this is the discrete time Fourier transform pair. For this signal, the Fourier transform is this. Okay, and its magnitude will be this Okay, you can just expand the e to the power minus j omega term with the help of Euler formula, and then you can take out the mod of this expression very easily. So there are some facts for this magnitude, that if a equals to 1, okay, a is comparable to 1. Okay, now let's see. Now let's put the value of a here. Okay, it is 1 plus 1 2 minus 2 cos omega. Okay, then it is tending to 0. Oh, sorry, tending to 1 only. That it implies that x of n is comparable to un. Okay, this signal varies slowly. It means that it has non-zero spectrum around 2 pi k. Okay, as you can see that for around 2 pi k 0 0 it has non-zero spectrum. Okay, and if a is comparable to minus 1, then x of n is comparable to minus 1 to the whole power n u of n. Okay, and this signal will be fast varying, which means that the spectrum will be concentrated around pi plus 2 pi k. Okay, so if I put the value of k 0 here, then you can see that it will be concentrated around pi. Okay, so this was the example. Okay, here one thing that is needed from you students, which is that I will suggest that you memorize this discrete time Fourier transform pair, because this will come handy when you will be solving complex problems, because this expression will be there and you might not, or you did not want to solve it, because, or you need not solve it because you already know the Fourier transform for this expression, so you can easily write it. Okay, so this will help you to reduce time in your problem solving. Okay, so now let's see the second example, which is a unit impulse. Here the x of n is equals to delta of n. So if I try to find out the Fourier transform, okay, which is x of e to the power j omega, summation n equals to minus infinite to infinite, x of n e to the power minus j omega n. Okay, as you all know that delta n will be valid for n equals to 0. So if I put n equals to 0 here, then it will be equals to 1, implies that the Fourier transform for the unit impulse is 1. And these are the plots of the curves of the signal original and then the Fourier transform signal. Okay, the next example is shifted unit impulse. It is similar to the shifted unit impulse of the continuous time case. Okay, but I am going to teach you. As you can see that x of n is equals to delta of n minus n naught. So if I put the value of say n equals to n naught, then it will be valid only. Okay, so there are two ways to see this equation or to solve this equation. One method is just like the unit impulse, where you can see that delta of n minus n naught will be valid only for n equals to n naught. So if I put n equals to n naught here, the delta function will be 1 and e to the power minus j omega n naught will be remained out. Now other method is that you replace n minus n naught with k. Okay, so it will be delta of k and then it will be e to the power minus j omega n minus n naught is k. Okay, so n will be equals to k plus n naught. Okay, with the minus outside. So you can take out the term e to the power minus j omega n naught, which is a constant term, and now you can replace the k with n, so you will get this term, the term of the unit impulse, okay, whose Fourier transform is 1. So again you will get this term as your Fourier transform for the shifted unit impulse. Okay, and these are the curves for this transform. Okay, this is the curve for signal, which is delta of n minus n naught, and this is your magnitude spectra related with this, and it is your angular or phase spectra related with the shifted unit impulse. The next example is the rectangular pulse. Okay, so as you all know that rectangular pulse is just a rectangle defined between two values on the curve. Okay, here I have x sin equals to 1 for n mod n less than n1, and it is 0 for mod n greater than n1. So as you can see that it is the rectangular pulse. So if I try to find out the Fourier series, the Fourier transform, sorry, okay, then it will be summation n equals to minus n1 to n1, because the signal is valid from minus n1 to n1 only. Okay, e to the power minus j omega n. Okay, here xn is has been put the value 1. So I can take out e to the power j n1 omega. Okay, and change the limit like this. Okay, this is the property of summations. So when I solve this exponential sum, then I'll get a term like this. Okay, so when I multiply this term with this term, I'll get this type of expression, which I can reduce to sine expressions. Okay, so now you have reduced this to sine expression. Okay, then it will be easier to solve. So as you can see that this is your curve for the Fourier transform, which is a sine upon sine function. Okay, so this was all in the examples. Now let's see the convergence of discrete time Fourier transforms. So there are things different in this discrete case than the continuous case. Okay, so the Fourier transform are also valid for signals which are of infinite duration. Okay, and the sufficient conditions for convergence are again the one condition, which is the signal should be absolutely integrable. It was in the continuous time case, but now it is absolutely summable. Okay, and the second condition is it should have finite energy, and there is no convergence issues with inverse discrete time Fourier transform, and there is no Gibbs phenomenon related with the discrete time Fourier transform. Okay, this was all from my side in this tutorial. In the next tutorial, I'll start with the next topic, which is the Fourier transform for periodic signals. As I have told you earlier, that there are two categories. Which the one is for the sinusoid signals, which consists of sine and cos function, and then the other category, which is for other periodic signals. Okay, which I will teach in the next tutorial. So thank you guys for watching. I'll see you in the next tutorial.